Okay, this is the second hour of Physics 1C for March 27th. And we just talked about how to find the magnetic field for a wire. And we found the value. We'd like to kind of look at how magnetic fields add together, though. So the next one we're going to do is the magnetic field of multiple wires. We're going to find the magnetic field at 3 different locations, 4 different locations. We're also going to do one more than shown on here. And so for this one, I already drew out a picture. So here's our picture of what's going on. Let me make it a little bigger. Okay, so we have 2 wires, wire 1 and wire 2, that have current I1 and I2. The currents are going to be the same as each other, but we're labeling them differently so that we can use them to describe things. So it says, this figure is an end-on view of 2 long, straight, parallel wires perpendicular to the xy plane. Each, so the xy plane would just be the plane of the screen. Each carrying a current I, but in opposite directions. Find the magnetic field at points P1, P2, and P3. So P1 is a distance of 3D away from I1. P2 is right in between I1 and I2. And P3 is to the right of I2 by a distance of D. And then these two are separated by a distance of 2D. Okay. We want to find, and then we also want to find an expression for B at any point on the x-axis to the right of wire 2. We're also going to try to find the magnetic field somewhere up here, too. All right? So that's what we want to do. Okay. Let's start at point 1 right here. Can get rid of all this garbage that's inside of here. Enough clicks. I want to get rid of that one. Okay. So at this location, and let's write our formula up here because this is the formula we're going to be using the whole time. B is equal to where R is the distance from the wire to the point. So at point 1 right here, what's the direction of the magnetic field created due to wire 1 at point P1?
Downwards.
Down? Okay. Now, if you're having a hard time understanding how to do this, the way I think about it is this. If you draw a circle and you make it so that the center of that circle is right on the center of the wire, like kind of like this basically, like that. So I put the circle in the center of wire 1 right here. Then the direction of the magnetic field at point P is going to point tangent to this path. And the direction is given by the right-hand rule. So since this current is coming out of the page, the magnetic field is going to be kind of sweeping in a counterclockwise direction around here. So the magnetic field, for example, at the top right here would be like, I did not want to move that. The magnetic field, come on, get off. The magnetic field up here would point this way, and if you go down here, it basically points down this way, right? So let's get rid of that. But that's kind of how I try to think about it. Let me select this, and let's get rid of this. Okay, so if I draw that as a vector, let's use blue for the fields on this one. The magnetic field is going to go down this way. And I'm going to call that one B1. What's the magnetic field due to wire 2? What direction is that going to point?
Upwards.
Up.
Yep. So we're also going to have a magnetic field that is going to be pointing upwards. It's going to go up this way. Which one's going to be bigger, I1 or I2? Or B1 or B2? Which one's going to be bigger?
B1.
B1, and that's because we're closer to B1, and it falls off as 1 over the distance, right? So the farther away you get, the weaker it's going to be. So B2 is going to be pointing something up like this. They're both vectors. And if I want to find, let's call it the net magnetic fields at point 1, then this is going to be equal to the sum of the magnetic field created by B1 plus the magnetic field created by B2. Just like all other vectors in physics, if we know the vector field for one, then we know the vector field for the other one. The total vector field is going to be the sum of the two, or the net vector at that location is the sum of the two vectors at that location. Okay, so they're in opposite directions, which means that if I want to find the magnitude of the net magnetic field, then what we're going to get is for B1, it's going to be mu naught times the current. Now remember, the currents are the same. They're both equal to I. So it's mu naught times I. You divide by 2 pi, and then you have to divide by the distance from point P to this point, which in this case is 3d. All right. And then, this was B2, right? So B1 is going down. Let's make this direction the positive y direction, which means we're going to need to make this first one negative then. For B2, we're going to have mu naught times I. We're going to divide by 2 pi. And now we have to divide by the distance from this point to I2, which is going to be 3d plus 2d, which would be 5d. And that gives us something like that, which we can simplify. Does that make sense?
Mm-hmm.
You don't have any questions? So a fifth minus a third is going to be 5 minus 3. No. 3 minus 5 over 15. So 2 over 15. So I think this whole thing is going to be equal to... Is that right?
Yeah.
Okay. So that's the magnetic field at 1. At point P1. Let's do the other 2 points. So at P2, what do you predict the magnetic field at P2 is going to be? You think it's going to be 0, you think it's going to point up, or you think it's going to point down?
Oh, was this in terms of I1 or I2?
Total.
Oh.
What do you predict before we look at what you get for I1 and I2, and you can certainly think about it yourself if you want to. What is the direction of the net magnetic field in this case going to be? Is it going to be 0? Is it going to be up? Is it going to be down?
0.
All right, let's see what we get.
0 as well.
I think maybe not.
You think up? Okay, let's see what happens. So what's the direction? Let's do it one at a time. The magnetic field created due to I1, what direction is it going to point at point P1?
Upwards.
Okay, so that's B1. And again, point your thumb in the direction of the current. Your fingers are going to rotate in the direction of the magnetic field. And then the magnetic field due to this one, I2.
Also upwards.
Also up, yeah. They're both going the same direction. Should they be the same length?
Are
Same
the
distance,
carrying equal? Yeah.
The currents are the same, the distance is the same. That means that the magnetic fields are actually you would expect it to be 0, kind of like, because if this was a positive charge and this was a negative charge, the field in between would also not be 0, actually, right? Because like if this is a positive charge, the field would go to the right. If it's a negative charge, it would go to the right. Would also, so it's the same kind of thing. The current coming out and the current going in are like a plus and a minus charge in a weird way, you know? Yeah. Now, if both of the currents were pointing in the same direction, what would the direction of the field be? Like
Then
it would be 0, right?
0.
Just like if I have a positive charge here and I have a positive charge here and I come to some point in between, we know the electric field at that point is 0, right? Okay. But if they're different, then it's not, right? If I have a positive charge and I have a negative charge and I come to this point right here, well, the electric field actually points this way. Because both of them create an electric field vector that points like that. So that's just to kind of tie what we're doing back. Because it's a very similar kind of concept. That now, with electric fields, what was the source of the electric fields? It was electric charges, right? Now, what's the source of the magnetic field? It's currents. It's electric currents. So B net in this case is just going to be equal to B1 plus B2. They're equal to each other. So if I want to find the magnitude, this is going to be mu naught I over, and I think the distance is d in both cases. So it's d here, and then plus mu naught I 2 pi d. So our final answer here is going to be mu naught times I divided by, I think half plus a half is 1, so just times pi d. Okay.
So it looks like, so I mean, currents in this configuration would want to push away from each other.
Well, we haven't talked about that yet.
Okay.
But you're thinking about the force on a current carrying wire,
Mm-hmm.
and you're thinking, oh, well, now this electric current must produce a magnetic field also at this location right here, right?
Yeah.
And it would go up as well, right? But then you think, oh, wait, but we learned last week that if I have a wire and it carries current in this direction, and I place it into a magnetic field that points up, then according to my right-hand rule, I go and I get a force that's to the right on this current carrying wire. That's what you're thinking about?
Yeah.
That's 100% right. That's the next topic. That's exactly where we're going to go next. These two wires are in fact going to repel each other. So now it's actually the opposite of the way it works with currents, with electric charges, but we'll get into that next. These two things actually would repel each other, though. And we're going to look at an actual demo of that pretty soon, too. Okay, P3. Okay, point 3 is right here. Now again, what's the direction of the magnetic field vector at point P3 for I1? How do I draw B1?
Up.
Okay, up, you say. I think that's correct. And now you can kind of look over here. With our first picture, it was down, right? Because again, the current's going to create circular magnetic field lines that are going to go counterclockwise like this. So if it's down over here, it's up over here. So that's going to be B1. And then what about B2? What direction is that going to point?
Down.
Down. Which one's bigger, B1 or B2?
B2.
Yep. So there's B2. Okay. Then once again, we're going to say the net magnetic fields is now going to be equal to, again, B1 plus B2. And B1 is going to be mu naught times I divided by 2 pi times the distance, which is now going to be d, so 3d. And B2 is down, so we'll put minus. And then the distance is just d. So this one ends up being mu naught I over 2 pi d times. The first one has a 1/3 minus 1, which means this one is going to be equal to, I guess I have a little bit of room here. Mu naught I, 1/3 minus 1 is 2/3, so so we just get mu naught I over negative 3 pi d, right? There we go. That's the magnetic field at each of those points. Does anyone have any questions? It's all pretty easy, right? It's not, maybe it's not easy, but it's not that hard.
Just the sum of forces.
Pretty intuitive.
Sum of vectors, we're just summing vectors, just like we always do in physics, yeah. Okay, the last, part B says, so all of this was part A. And then part B says, find an expression B for at any point on the x-axis to the right of wire 2. So there's a little bit of room in here. So let's say we come to, oh wait, we used red for the currents, didn't we? So let's just come to another point right here. We're using green for the points, right? So let's call this point point 4. And it says at any point on the x-axis to the right of wire 2. Now, I think I left something out here. I think in the original picture for this, the y-axis was pointing this way, and the x-axis was pointing this way, which means I think that the middle point where these two are right here is 0, 0. So this is the origin right here. Point 2 is the origin, which means point 4, we can start off by saying the distance from here to point 4 is going to be x. And we want to come up with an expression for the magnetic field at any point on the x-axis to the right of wire 2. Okay? So we just call that distance right there x. In that case, we already kind of know the directions now, right? We know that B1 here. Can we get rid of here? Yeah, can I get rid of just this one? Or should I? Let's just shift it over. We know that B1 is now here. Come on, select both of those. B1 is now pointing this way, right? And B2 is still pointing this way. Let's get rid of the part that says P3 if I can. Okay. And then, boy, it's just it's not ideal. Come on, let me click the two. There we go. All right. So, this just got really bad here. Let me just, that's P4. It's a distance x away. We know B1 is up and we know B2 is down, right? So, the magnetic fields for point 4 is going to be, once again, we're going to need to do B1. So B1 is going to be mu naught times I divided by 2 pi. And I would say the distance to point 1 now is going to be d plus x, because we're looking at this point here now. Is that clear to everyone?
Mm-hmm.
And then I think the other one's going to be like x minus d or something like that. And we have to subtract mu naught I over 2 pi. So it's x minus d is going to be the distance to I2. Can everyone see that? And just because I'm obsessive, I prefer to write this as x plus d so it looks symmetrical. All right, does that look right?
Yep.
And then we just, group terms. Mu naught I over 2 pi times 1 over x plus d minus 1 over x minus d equals, I guess I have a little room to keep going here. I don't want to run too much into this though. So we'll just go down. We'll just go down. So this equals what happens to the numerator now? X minus x, negative d minus d. So we have a negative 2d left over, I think. And then the denominator is x squared minus d squared. And then this is just going to be negative. Well, we could absorb the negative in the denominator, I guess. So it would just be, Yeah, x is always greater than d, right? Maybe we shouldn't do that. Yeah, just leave it as negative mu naught I d. The 2's cancel. And there we go. That's our answer. That would be the magnetic field as a function of x, basically, away from the wires.
There's still a pi in the denominator, right?
There is still a pi. Thank you so much. Yes, there's a pi right here. Yep. You have any questions? This last question is kind of more mathematical. I guess we could also probably look at like what happens when x is much, much greater than d. Is that interesting? Not really, right? Maybe it is. Kind of is, actually. Because if x is much, much greater than d, then the magnetic field falls off as x squared, 1 over x squared, right? Whereas the this is kind of...
That's true.
It's like exactly like the point charge, right? Or dipole, sorry, dipole. Because with a dipole, the magnetic field falls off as 1 over, like, x cubed with charges. Do you all remember that?
Mm-hmm.
But the field of a point charge falls off as 1 over x squared, right?
Mm-hmm,
So it's 1 power higher, right? The magnetic field of a wire falls off as 1 over x, but the magnetic field of 2 wires that are pointing in opposite directions falls off as 1 over x squared. So it's also exactly 1 power higher in terms of how quickly it falls off, right? That's kind of interesting. It's not like, I don't know, finding gold or oil or something, but it's kind of interesting. Okay. Anyone have any questions? Do some vector addition. Basically, all we did was, for the first hour of class, we derived this relationship, which is really simple. And then for the second hour, or the second 30 minutes or whatever, we've done this one problem. But that's okay. That's good. You know, it's funny. In Physics 2b, we would do problems just like this in Physics 2b, which is it's like the second half of Physics 2a, but, you know, most people don't take it. And it's kind of funny because we end up doing a lot more problems because I don't have to derive stuff. Because there's no way they could go through all this stuff and understand anything that we did here because I can't use calculus, and even cross products are too much for them, probably. So it's interesting because we get to cover more material in a way in that class because we don't do any derivations. So it's kind of too bad that we don't have students take Physics 2b. You might be really well you would be very well prepared for Physics 1c if you had already taken 2b. You really would, because then we could just spend most of the time going into like the harder details, you know. Anyway, just kind of an aside. All right, what's next? I think next we do the circular wire, right? Oh no. What Cam mentioned, the force between parallel conductors. That's what we want to do next. So Cam noted that, you know, when he's looking at this problem right here, he kind of realized that, this wire creates a field, and it creates a field at this location too, and then magnetic fields produce forces on current-carrying wires. So there should be a force here, right? And so that's the exact thing that we want to address right now. The force. Okay, so we're going to take 2 wires that carry different currents. So one wire is going to carry currents in this direction. And then parallel to it, there's going to be another wire that carries current in the same direction. Let's get plenty of space here that we can actually write some things down. So this one is going to carry a current that we're going to call I1. And the bottom one is going to carry a current that we call I2. To begin with, we're going to make the wires have current pointing in the same direction, but then we'll talk about what happens when we flip the direction of one of them. So there's basically 2 possibilities. Either the currents are flowing in the same direction, or they're flowing in opposite directions, or I guess there's no current. Those are the possibilities of what you can have. So we'll just look at this one first. Okay, remember that we have this expression that we've derived already, that the magnetic field created by a current-carrying wire is mu naught times the current divided by 2 pi times the distance away from the wire. So we've already got that we can use for this. So if I come to where wire 2 is located right here, what's the direction of the magnetic field at this point due to wire 1? Is it into the page or out of the page? The magnetic field created by wire 1 at the location of wire 2.
Into the page? Into.
Well, I got to put one other thing on here. The distance between the wires is A. Okay. Right? We want to use A? I think that's what we want to use. Okay. Into, exactly. So the magnetic field, B1, we would say points this way, right? And we also know that the direction of the magnetic field due to wire 1 is the same at every point on here. And as long as the wires are parallel, what does parallel mean? Parallel means that the distance between the two lines is constant. It never changes, right? The two lines never meet each other, which means they never get closer together and they never get farther apart. So the distance between them is constant. And that's important because that means that, based on my definition of what the magnetic field created by wire 1 is, the magnetic field at every point on wire 2 is going to be the same, right? Because they're parallel. So there's the magnetic field created by wire 1. Now, let's do the reverse. What's the direction of the magnetic field created by wire 2 at the location of wire 1? Is it out of the page or into the page?
Out.
Out. So I could come along here and say, I could put a bunch of little dots, and where a dot represents coming out. I'm not going to write as many as I did for the other one. But this would be the magnetic field created by wire 2, and it's going out of the page, right? Okay. Now, the other piece of this that we need, that we learned in the last class last week, is that the magnetic force produced on a current-carrying wire due to the magnetic field is given by this expression right here. And why that happens is because we know that charged particles, as long as they're moving, they feel a force due to magnetic fields. So if I have a current-carrying wire, it has charges moving through it, and the wire itself is going to feel a force that's equal to I times the length of the wire, I is current, multiplied by the size of the magnetic field. Okay? Now, part of this means we need to know the length of the wire. Okay, so now we need to introduce another piece of this, which is I'm going to say that our wires have a length L. Let me leave plenty of room down here. So the length of our wires is going to be L between this point and this point here. It just looks so bad. I'm not going to do that. We'll just use a line. Here, we'll use this one. So this distance now is L. And let's just use a tiny eraser here and just say that this distance is L right there, because that's part of our definition right here. Okay, and the direction of the force, I left off a vector, is going to be L cross B, right? Remember that L is basically just a vector that points in the same direction. L is a vector that points in the same direction as the current, right? So this would be like the direction for 2, and this would be like the vector for 1. It would point like that. So let's use our equation right here and say that F, how do I want to write this? The force of 1 on 2, and let me even write the whole subscript out so it's really clear what I'm saying. The force of wire 1 on, no, that's not the right way to put it. It is the right way to put it though, isn't it? Yeah, the force of 1 on 2 should be equal to the current flowing through wire 2 times its length vector cross products with the magnetic field of the other object, right? The force that the magnetic field B1, that's how I should write it. I should write it as, because this gets kind of tricky. The force of B1 on I2. That's how we should write that, right? Is that clear? The magnetic field B1 places a force on wire I2, and it's given by that expression right there. Does what I've written there make sense to you all?
That looks clear.
Okay, so let's start plugging some things in. Because one thing we know is that B1 is just equal to mu naught I1 divided by 2 pi times the distance from this point to here, which we're calling A, the distance between the wires. So we actually know what B1 is, right? In addition, we can talk about the direction, so we can get rid of these vector things. What's the direction of the force created on wire 2 due to B1? If you use your right-hand rule. So you do I cross B1, it's up, like Kyle said right there in the chat. So the force, kind of running out of colors here, the force is going to be pointing upwards. That is the direction of our force. We'll call it the force of B1. Okay, so since we have the direction taken care of, then we can just write F of B1 on I2 is going to be equal to the size of the current I2 multiplied by L2, which is now just going to be the magnitude of L2, which is just L. Cross product with B1. Well, B1 is mu naught I1 divided by 2 pi A. And now I'm going to drop the subscript right here, and I'm going to write it like this. I'm going to say the force per unit length is equal to mu naught multiplied by I1 times I2 divided by 2 pi A. And that's our answer. The force per unit length is equal to the product of the currents divided by 2 pi times the distance between them, and then multiplied by mu naught. And these two wires, it appears at least, it appears that I2 is attracted to I1, and keep in mind that this force is everywhere. This same force is pulling on the entire wire, because the wire is composed of tiny little charges, right? And if we go back to the other wire, we can figure out what's going on there too. Again, look at this equation right here and say, what's the direction of the force of B2 on I1? So you go, I1's this way, twist your hand upside down, flip your hand this way, and the force is going to be down, right? Can everyone see that? So the wires are attracted to each other.
Interesting. It's kind of like a pressure, or but not quite pressure.
Are you thinking of the Bernoulli effect when you like blow between two cans and they come together?
I was thinking more like force per unit length, but that's interesting too.
So the general rule of what happens here is that the wires are going to basically attract each other when the currents flow in the same direction, and they'll repel each other when the currents flow in opposite directions. You know, if you pick up any wire, I don't have a good example because it's close to me, but I'm thinking about like the wire that connects my what's it called? My lamp in my bedroom. It has like a wire that's kind of split down the middle. I can kind of draw a picture of this because I'm sure you all have seen these before. Have you all seen these kind of wires that are like, it's like one little tiny wire, and there's basically a split right down the middle so that it looks like two little tiny wires that have been kind of like merged together, and then, you know, they go into like a socket that plugs into the wall. You all know what I'm talking about?
Yeah.
Okay. The wires here actually have current flowing in opposite directions. So there's a current going this way, and there's the current that comes back that goes this way. So technically, these wires would feel a force that would attract each other, but they're composed of all of this. Repel. They would repel each other, right? But the size of this force depends on the currents. So the bigger the currents are, the bigger the force is going to be. It also depends on how close together they are. If they get close together, it gets bigger, but then it's suppressed by this number because this is 10 to the minus 7. Anyway, so that's what happens when you get two wires that are near each other. They feel a force.
That is interesting though. What you said, it is kind of like Bernoulli. I like the pressure thing.
Mm-hmm. So let's go to YouTube. And I'm going to show you all this video. I had this pulled up last week because I thought for some reason we were going to show this last week, but we obviously didn't get to it. So we're looking for that one. No. Yeah. Here it is. So we have this same setup at our school. I'm going to have to switch this to where Here you go. This is a pretty short demo, as you can see. But this is the force on a current carrying wire. I think this is the right one, right? Yeah, this is it. Okay, so here we go. In case it's not obvious what he's saying here, because it's probably not obvious, but parallel, I think, means that the wires are carrying current in the same direction. Let's just see if that works. What happens when parallel? Are they attracted or repelled? Oh, we gotta go back now. Yeah, parallel's attracted. Is that what consistent with what I said?
Mm-hmm.
Yeah. Attract, same direction, right? And series means the current would basically be flowing up one and then down the other one. So they would be flowing in opposite directions. But yeah, that's pretty cool. You have to have really, really big currents to make this work. Now, they're doing this just with a 12-volt battery, aren't they? That's kind of impressive. Because I'm pretty sure the one that we use on campus is, it's not just a battery. We do it with like a really high-powered thing. Maybe we need to switch over to using a 12-volt battery, because this looks a lot less dangerous than the setup that we use at the school. But anyway, there they go. It's kind of crazy to see that happen. It just feels. I always feel these demos, especially with electricity and magnetism, are really. I don't know. It's like really counterintuitive to see. Here, I'll just stop it. He's gonna flip a switch, and these two things are just gonna bow apart from each other. Just two wires, and there's no physical contact that's making that happen. There's no wind that's making it happen. It's just that's how electricity and magnetism works. You get a bunch of negative charges flowing in one direction. Gotta remember again. They repel when opposite, right? So this is saying that if I have a bunch of electrons flowing down this way in one wire, and I have a bunch of electrons flowing up this way in the other wire, they repel each other. And it has nothing to do with the fact that they're electrons. It just has to do with the fact that there's like current flowing, Because electrons should technically always repel each other, right? They should always repel each other. But maybe the repulsion force between the electrons in this one, they don't feel it because there's also positive charges, right? So even though I have negative charges flowing down here and negative charges flowing up here, they don't repel each other because there's also positive charges there, at least not due to the electric force. But the motion of the charges themselves produces magnetic fields that affect the other object. Or at least that's the way we talk about it. Do we have any questions or comments?
They look disturbingly alive.
Yeah, they do, don't they? They really do. I would agree. Back to OBS. Yeah, that's how I feel too, is like, that what's happening is the result of physics, but nonetheless, they appear to do something that is lively. Like, saying that they're alive sounds good, because living things can obviously move. Like, I can move my hands around. I don't need some external force to like push my hand and move it, right? But an electric wire, you need some external force to make it move, because it's not animated, right? It doesn't have its own force of will or whatever.
Kind of looks like muscles contracting and restricting.
Yeah, something like that, yeah. Which, at the end of the day, you could ask yourself, well, how am I actually able to move my arms and stuff like that? And the answer is because of, well, electricity and magnetism. So like, that motion you see of those wires bending apart is a representation, okay, fundamentally, of how everything moves. Right? I mean, the only reason I can move my arm is because there's like an electrical impulse that's sent from my brain to the muscles of my arm that tells them to start contracting and moving in a certain way, right? And even the forces that control how my muscles contract are electrical, you know? So saying that it looks like that thing is alive is a pretty good way of describing why it looks so weird, is because we're not used to seeing things that are dead move, you know, of their own, like, willpower. Okay, so do we have time to do some more stuff? I think we do. Are we on Ampere's law? Oh, well, we could do this. Let's do this calculation real quick. Really easy calculation. So we can see the formula right there. We have two parallel wires. They're 4.5 millimeters apart. They carry equal currents of 15,000 amps in opposite directions. What force per unit length does each wire exert on each other? Okay, pretty easy to do this calculation. So the force per unit length is equal to mu naught, which is 4 pi we multiply that by the current, so one current is 15,000 amps. The other current is the same. And we divide that by 2 pi times A, which is 4.5 millimeters, so 4.5 times 10 to the negative 3 meters. Should be able to do this on the head. Maybe. 15 over 4.5. So this is like 45 times 10 to the negative 2. 4. Is that the answer? That can't be right. Oh, and then you have to multiply by 10 to the 3 twice. So this is going to be maybe this. Is that right? What do you all get?
I got around 10,000.
10,000. I'm completely wrong, basically. Nope. So you got about 10,000 newtons per meter. 15 divided by 45 would be 1 over 3, right?
Yeah.
Yes.
And 15 divided by 3 would be 5. Oh, 5. 5 times 2. Not 3 times 2. 5 times 2. Yeah, 10,000. That's right. I agree. Okay, force per unit length is about 10,000 newtons per meter. Now, these are ridiculous values of current to get this size of a number, but, you know, there it is. Okay. Let's finish up with the last thing we'll do with the Biot-Savart law, which is to find the magnetic field of a wire like this, a loop. Because we can produce magnetic fields not just by having straight wires, but also having loops of wires. Oh, there it goes. So suppose I have a wire that's oriented like this. And instead of drawing this myself, I'm just using the picture from... This is probably from your textbook, given all these nasty artifacts that show up when I copy it. Because I just can't... I can't draw what's drawn here in 3 dimensions. It's just really, really difficult. We could look at a cross-section, but... Okay, so I've got a current. You can see the axes here. The x-axis is coming kind of out this direction. The y-axis is up, and the z-axis is pointing to the left. That's the positive z. We have a loop that is formed into the shape of a circle. It might not look like a circle, but we're going to pretend like that's a circle. The radius of this loop is A, and we're looking to find the magnetic fields on the axis of this loop at point P right here. Okay? That's what we're trying to do. And they've been nice enough to draw for us the dl vector, which points this way, as well as the r vector, which is going to point from dl, remember, down to this point right here. And what we have to do is somehow find a way to use this ugly equation, dB equal to mu naught I over 4 pi dl cross r hat divided by r squared. You know, the first time I remember teaching physics, and this goes back to like about 2010, I think, so almost 11 years ago now. I remember the first time I had to like explain this to students, and I did such a horrible job of it. I'm sure I'm not doing a great job today, but I can promise you it was better than the job that I did that day. I just didn't have any way to describe to students like how to do these kind of calculations, this dl cross r hat thing. But after 11 years, it's not so bad anymore. I feel like I understand it, but my God, that equation still looks awful when I look at it. You know, dl cross r hat. You have to do a cross product, and then you have to do an integral with it. Like that's about as complicated as anything can get in terms of you know, vector fields and all this kind of stuff. At least with physics, I'm sure it gets much more complicated in your mathematics classes. But anyway, so r goes this way. dl's this way. We have to figure out the direction of the magnetic field at this location. That's already kind of been done for us. It's in the picture, it's showing us that the magnetic field at this location is kind of pointing off like this, basically at a right angle to r. Now let's see if we can convince ourselves why that's true. So in order to do that, we have to do this process of doing dl cross r hat, right? So if we look at our picture right here, let's see if I can do this. dl is this way, right? But r kind of points kind of down towards p. So if I do dl cross r, my thumb is going to point up at a right angle like this. Now remember that when I do a cross product, the vector that I get as the answer, which in this case is dB, has to be at a right angle, right, to both of the other vectors, right? So dl cross r, when I do that, this vector, which is equal to dB, what this tells us, or proportional to dB, or whatever you want to say, is that the vector dB, right, it has to be perpendicular to r, and it also has to be perpendicular to L. Oops. To L. Or dl, sorry. So can you see how in my picture here that dB is perpendicular to r? That means that this is a right angle between here and here. Can you all see that? R,
Yeah.
dB. And then the next part's probably not so obvious, but could you convince yourself that dB is also perpendicular to dl? If we were to take this dB vector, which is kind of pointing, it's hard to draw here, but it's kind of pointing, you know, kind of like that, right? Again, you can see how it's perpendicular to r. That's easy to see. But you also need to be able to convince yourself that this is actually perpendicular to that one too. But that's not that hard to believe, right? Because any vector that I would draw, so take a ring like this. Take a ring like this. Say it carries some current I like this. Draw in your dl vector like this right here, right? Pretty much any line that I draw, like, here, let me draw a simple line. This line is easily perpendicular to this, right? But now take that line, which is pointing up like this. You can rotate it like 360 degrees around the current, and every vector that you draw would be perpendicular to dl, right? Do you all agree? Any vector that I draw, whether I draw it up, or whether I draw it coming straight out of the page, or straight down, or even at like a 45-degree angle, it's still going to make a right angle with dl, because dl, here, I guess I can use this. So dl is this way. Can you all see this pen? You think you can, right? I'm not really, like, I can only see half of my camera. So if dl is this way, and I'm saying I want to draw a vector that's perpendicular to it, basically I can rotate this through 160 degrees, and these two vectors will still be perpendicular to each other. So saying that, and then looking back to this picture right here, can you convince yourself that dB is also perpendicular to dl here?
Yep.
Okay. All right. So now that we've done that, we've got the direction out of the way. Hopefully everyone understands why it's pointing kind of up at this weird angle right here. The next thing to do would be to say, what if we went to the opposite side right down here and we draw in our DL vector now? So now if I come down to the opposite side over here, the DL vector has to basically point... Oh, no. I'm going to draw it kind of straight. The DL vector basically has to be basically the opposite direction as is up here. Oh my god. When I try to shift where I'm writing, it just gets so much harder. I like to be very actively moving while I'm describing things, and this doesn't work out well. So there's DL, right? Now, if I draw my R vector out to here, can you all tell me what direction is DB going to point now? What direction is DB going to point now?
Downwards.
Yeah, down.
Like slanted.
It's going to be DB now. I'll use a different color because I don't want it to like clash so much with what's going on there. So DB now, it has to be at a right angle to this one, right? And it's going to kind of point down like that, right? And now the argument I would make is, since I picked a point that's exactly 180 degrees opposite from the other one, to figure out the direction of this one, or more specifically, if I want to figure out the direction of dby in this case, dby is going to have to point exactly in the opposite direction, right? And if you have a hard time visualizing this, all you really need to do is to look at the direction that dby is right here and say, if I go 180 degrees around to the bottom, that would be like taking this vector and rotating it 180 degrees around to the bottom down here, right? Which means that this dby and this dby have to be the same as each other. Just one is up and one is down.
They'll just cancel.
They'll cancel, yeah. So what's going to happen is that, just like what happens in a lot of these problems, the dby's all cancel. And all we really need to calculate is dbx. That's all we need to do, is just to find the dbx. So I'm going to erase all these lines that I've drawn here. But does that make sense? If I go 180 degrees to the opposite side, the dby is going to be down now, and they'll cancel out. But the dbx's, all the dbx's are going to point along the positive x-axis, right? Because now let me get rid of all this stuff and talk about how you could have figured this stuff out just using symmetry. If I take this system right here, which right now, the way it's oriented is I've got my ring off here to the... Oh, no, wait. This must have been so confusing for you guys all day. This thing's not mirroring. Can I fix this real quick? Will it let me fix it during the stream? I'll try to remember to do it after the stream. Because OBS got rid of my... I need to I have to flip the mirroring on the camera. Whatever. Doesn't matter. Point is that if... yeah, so if I want to point something... Yeah, it's exactly opposite. Dang it. Alright, whatever. Point is that you could rotate this around 180 degrees, dB wide, point down. I think I've beat that horse to death anyway, so you probably get the idea. Select. Let me select. Just want to delete this. Let me... Cut. There you go. Okay, so now let's do the calculation. So, we want to find dbx, which means if we call this angle theta right here, which is the same as the angle theta that shows up here, you can convince yourself of that if you want to, then I would say that dbx should be equal to db times what? Cosine theta? And that's going to be equal to mu naught I divided by 4 pi. Now, once again, we're going to need to do dl cross r, but I'm pretty sure that they're at right angles to each other now, right? Would you all agree that this has to be a right angle right here?
Yeah.
So I think in our problem that dl cross r hat, oops, is just going to end up being, well, the magnitude of dl is just dl. The magnitude of r hat is 1, and if they're at right angles to each other, it's just dl, basically, right? So we have dl divided by the radius squared and then multiplied by the cosine of the angle theta. Now, is the angle theta going to change as we go around this circle right here? So say we come to this point right here, and then I draw a vector from here to here.
No,
It should be the same, right? It's going to be really hard for me to ever draw this, but one of these will go that way. Go up a little bit. This angle theta, which is made, again, you basically draw a line. You draw a line to here. The angle theta is right here. And yeah, it's going to be the same everywhere you go around the circle, even with that horrible drawing there. It's pretty clear, I think. Even they're three-dimensional, so they shouldn't look like the same angle, but it will be the same angle, right? Okay. So theta is a constant. What about r? R is also a constant, right? We know that r is equal to x squared plus a squared, square root. So that's a constant because x is just the distance along the axis. A is the radius of the loop. So I think everything is a constant, which means when we evaluate the integral, we're going to get that v sub x is equal to mu naught I over 4 pi r squared cosine theta. I guess we also want to write what cosine theta is. So cos theta is going to be equal to x over r, so x divided by that. So let's plug that in for cos theta.
Shouldn't it be a over r?
You're right. Absolutely. Thank you. Thank you. Mm-hmm. Okay, thanks for catching that. I really appreciate that. Okay, mu naught I over 4 pi r squared, a over, that's cos theta, and what are we left with? We're just left with the integral of what's left over.
It's just the dl.
Yeah.
DL. So now we just need to integrate DL, which is going to give us just 2 pi a, right? When you integrate,
True.
it's just going to be, so this whole thing is just going to be 2 pi a. And we can go ahead and plug in what r is now, too. I should have done that before. So 4 pi, so r squared is x squared plus a squared. And then we're multiplying that times x squared plus a squared to the 1/2. So we come, just like we always do, we get a 3/2 power down here. There's an a in the numerator. It's everything, right? So the pi's are going to cancel. There's an a squared in the numerator. There's a 2. And that is our answer. It always takes so many words to even say what we're doing. It's one of the things about physics is so hard. It takes all these words to even describe what this equation represents, but then the equation itself is quite complicated. Like if you gave this equation to a kid in 6th grade and be like, this is how you find the magnetic field of a loop of wire on axis at distance x from the center, then they're going to have all these questions about, well, what do all these words mean? Every one of the words I just said, what is magnetic, what's a field, what's on axis mean, they probably know what distance and center means, right? And then they'd be like, oh, okay, then what are all these things? And be like, well, this is the distance of the radius of the loop is a. X is the distance away. Mu naught is just a constant, and I is current, and you have to explain what electric current is. But, you know, this is what we do in Physics 1C. Does anyone have any questions? So that's a nice result. Now, there's a couple cool things that you can do at this. So one thing you can do is you can figure out what happens if I get multiple coils of wires and I put them next to each other. A common example of this is to take one coil of wire that has current flowing, let's say this way. Here, let's use the same direction as the picture. And then putting another coil of wire next to it. And I think you want it to point the same direction, right? Yeah. So let's say I have a current carrying wire that has a current I here and a current I here. And I come to a point that is along the axis of the wire. So like this is my axis here. Kind of goes straight through them. So I have one loop of wire here. I have another loop of wire right next to it. And right in the middle of these wires, there's going to be a magnetic field. And what's the direction of the magnetic field? Well, we just figured out that, let's see, that it's going to be left, right? For the one that I picked here, the magnetic field's going to point to the left. And I believe right in the center, the magnetic field, when you put two wires together like this, is going to be very, very nearly straight, basically, right at that location right there. And this type of arrangement is called Helmholtz coils. And we'll look at a demo of that here in a second. So the other application of this is, what I think is the simplest application of this, is to take this result and figure out what the magnetic field at the center is. So if you're at the center of the wire, now this is much easier to draw. So say that I take a wire, it has a current I flowing like this, and I come to a point right at the center with a radius A, I could ask the question, what's the magnetic field at that location? So the answer is going to be that the magnetic field at that location is going to point out of the page like this, right? And the size of the field, when x is equal to 0, this whole relationship reduces down to B equals, if x is 0, you have A cubed, which will cancel out with one of these. I think you're going to get mu naught times I divided by 2 times A. Does that look right?
Yeah.
Yeah.
But suppose that I take the exact same setup and I say, you know what, mu naught I over 2A, that's just not enough magnetic field. I want more magnetic field. How do I get a bigger magnetic field at that location? Okay. Well, the answer is, instead of just using one loop of wire, I can wind as many loops of wire as I want to in this same arrangement, and they can all have the same current flowing through them. If I then wrap, like, let's say, n turns of wire, then every single one of the turns, this looks like n tons. If I do n turns of wire, then every single one of the wires is going to produce this right here. So if I just drop an n on the front of here, then now I get the magnetic field at the center. This is a nice simple result. The center of a loop with n turns of wire. There you go. If you want to make it twice as big, use 2 turns. Make it 100 times as big, use 100 turns. You can also make it bigger by making the radius smaller, right? There we go.
For the Helmholtz coil, is it in your drawing? Is it pointing to the left or to the right?
Yeah, it's going to depend on which direction you think those currents are flowing. So if you see, as soon as I drew the magnetic field vector there, it actually makes it look like the currents are flowing up the backside and down the front side, right? Which means they would go the other way.
Mm-hmm. Mm-hmm.
So this drawing is just terrible, basically.
Okay.
It really is the perspective that was created by me drawing this line here made it reverse from the direction I was trying to do it. You know what I mean?
Oh, I totally see. Okay.
See what I mean?
Okay.
Because the current could either be going up around behind, like it could be going into the board and then out, Or it could be like, and I don't know if you can see this, but it could be coming out this way. It's like an optical illusion. It's an optical illusion. So whatever the direction is, you can reverse it by flipping the direction of the currents. We all agree with that, right? No matter what direction you pick here, if I just flip the direction of the currents, it'll automatically flip the direction of the thing. We're going way longer than I wanted to, but there was one other video that I wanted to show you. And again, I had it pulled up last time, but we just didn't get to it, so... I can't remember if this other video is really long. If it's really long, we might watch it next time. This one. This is what they look like. Let's see how long this is. It's only 2 minutes. Let's watch this video. So those are what Helmholtz coils look like. Right there. Two big kind of like armatures, maybe you might call this. I don't know, big metal frame. And I think you'll be able to see it when he starts the video here. But basically, do you see these red wires coming here? Each of these things has wires that are wrapped around to produce a magnetic field. And the goal with this setup is to produce a very, very straight magnetic field. Okay? You want to produce a really, really straight magnetic field. Okay, let's watch this video real quick, and that'll be the last thing that we do today. Change windows. Is it this one? Yeah, I think this is it. Let me know if you can't hear it.
Welcome to the demo prep room. We're sitting in the dark, but we're going to show you the charged particle beam does indeed go in a circle. Uniform magnetic field. So this is an evacuated glass bowl, and there's an electron gun in it. An electron gun really just means heated metal filament. It's easy to draw electrons off of. Near the gun, that you can now see glowing orange, is a little metal plate that we put at a large positive potential. That sucks the electrons up to a few hundred volts at the plate. The plate has a hole in it so that some of the electrons keep going and form a beam that continues on until it hits the glass. Now you're seeing the beam because it's exciting a little bit of gas that's inside the bulb. You're seeing light from the gas, but it's there because the beam is shooting through the gas. So you're seeing the electron beam indirectly. Now we know that if we bring a magnet nearby, it'll deflect the beam. So here's my north-south bar magnet, and sure enough, one pole pushes it up, another pole shoots it down. If I bring it in and do these kinds of things, you can do all kinds of crazy patterns with the beam. You can bring in a strong, concentrated magnetic field. But what we're here to do is to create a uniform field, and that's what these two big coils are. This is a large coil of wire on one side of the bulb, large coil on the other side. So if you put them together, you can make a reasonably uniform magnetic field on the inside. So this power supply is going to increase the current in these coils, and we'll see what pattern the electron beam takes. So here, we're going to start turning it up, and you can see it's starting to curve more and more. And right now it looks like it wants to make a circle, but the radius is too big. It doesn't fit in the bulb. So I keep turning it up, more and more current, bigger and bigger B field. Eventually, there it is. It makes a circle. Perfect circular motion, going right back to where it started. And if I turn the magnetic field back down to zero, straight again. So there's direct visualization of the circular motion of charge in the magnetic field.
So cool.
It is, right? I mean, and when he says he's changing the magnetic field, what's he doing? Oh, I'm sorry, Uzair. Did I unmute my mic during the thing to where you guys got really bad echo? I apologize. Yeah, he's changing.
Echo, but it's okay.
Yeah, I thought I muted my mic, but maybe I didn't push the button hard enough. I bet the echo got worse too because I turned the volume up, right?
You could just mute the stream and it still sound okay.
I just needed to mute my own mic was what I needed to do, so I apologize for that. I'll put a link in the video in case you want to hear what he was saying, but again, the question was, what's he doing to increase the magnetic field? And the answer was, he's just increasing the current, right? Like, because this is it. Mm-hmm. Look how simple this equation is, you know what I mean? Like, God, physics is so complicated, but the results are so simple sometimes, right? Like, yeah, there's some things in here you might not fully understand, like there's this constant, whatever. But you know what current is now, right? You know it's just flowing charges. And you know what... Oh, you're not seeing what I'm pointing to. Okay. Yeah, but like this equation controls all of what he's doing, basically, is what I was trying to say. He increases the current, the B field gets bigger. It's just that simple. And he knows the radius of the coils. This can be measured very easily. You can measure the radius of this thing, right? And you can see that they're pretty carefully designed, so I'm sure that the radius is fixed at a certain value. And then again, the place where the magnetic field is the most uniform, the most straight, is right in the center right here. Because as you saw at the beginning of the video, when he was just taking the magnet and putting it kind of at a random angle, did you see how the wire started to do these like coil thing, like these, yeah, like right there. See how it goes, and it's like it's going into this like helix pattern, right? Ooh, right. So instead of getting like that kind of like strange helical pattern, if you want to get just a perfect circle, you also need a perfect uniform electric field. So that's what that does for you. Okay, we need to stop because that was a very long second hour. It's like an hour and 10 minutes. So we'll stop right there. And